This is lecture number 18 on characteristic equation, eigenvalues, eigenvectors, and eigenspace. So this is a new idea and new concept. What we done in previous is a totally new thing. So we just start with what is characteristic polynomial. So there's a two thing. We know that if say V is a vector space, to vector space. So if any linear transformation is called operator. So any linear transformation from V to V, the same domain and codomain is called the operator. Now, if this is a finite dimensional, this V is a finite dimensional vector space, then under a basis, this T is actually correspond to a matrix. This T is correspond to a matrix A. So that corresponding that under that basis, the coordinate thing that if you write the, if you take say T is the linear transformation from V to V and T is a corresponding matrix. So corresponding matrix, how do you define that? So if you take any V with the coordinate with respect to that basis, this is just A into V with respect to that coordinate. So this is called the same thing, and that is actually the T of V with the same basis, coordinate with respect to the same basis. So we can talk about two different things: a characteristic equation of a matrix and characteristic equation of an operator. Now the basic difference is if you take a linear operator and it is a finite dimensional, then it is nothing is no difference. Basically, the corresponding matrix and that matrix, if the matrix characteristic polynomial or characteristic equation of the matrix is by definition, this is same as the characteristic polynomial of that linear transformation, that linear operator. But the problem is if the vector space is not a finite dimension, it's an infinite dimensional vector space, then there is no question of matrix. There is no question of corresponding matrices for a linear transformation. But we can generalize that idea of characteristic polynomial for a linear operator. How we just will say after this definition. So the definition with respect to matrix, say X is a matrix. Now X, that should be n cross n, because the linear operator for a finite dimensional vector space with dimension n, that matrix is n cross n. So the matrix should be square matrix. And just the definition of the characteristic polynomial is, we just take this xi minus the determinant of this is equal to 0. So determinant of xi minus a matrix is 0. So if A is your a1, a11, a1n, and an1 or ann, then this determinant is like the determinant x minus a11. Diagonally it is x minus a22, just x minus ann, and the others is same, x1 a1 to a1n, a21 a2n, and an1 an2, like that. So this determinant is 0. So it is a n degree polynomial. So it's a n degree polynomial. So what is characteristic polynomial of a matrix or characteristic polynomial of a linear transformation or linear operator of a finite dimensional vector space? There's a corresponding matrix, there's the corresponding matrix, and this polynomial, this is just this polynomial. You don't write as 0. Then that polynomial chi a of x. So this is just the polynomial, and this polynomial is called characteristic polynomial. And if you make it 0, so the equation is called the characteristic equation. Now, if V is a infinite dimensional, then there is no question of polynomial thing, because there is nothing about this determinant. But still, we can say about the characteristic equation. The characteristic equation will be there. So no, not polynomial, but you can talking about the characteristic equation. And the roots of this polynomial, roots of this equation, is called characteristic roots. Now, if the roots are, say, sometimes like lambda instead of x, if lambda 1, lambda 2, lambda n are the roots. Now, remember that roots are may not be distinct. The characteristic roots may not be distinct. Now, one thing is, two things is very important and easy to see, that the sum of these characteristic roots are the trace of the matrix, and the product of these characteristic roots are the eigenvalues. Sorry, are the determinant of the matrix. Now, this is easy to see. Why? Because if you just expand this polynomial, and you will see that we have this type, one term is like that, the product of all diagonal, and there are several terms also, but this is just degree at most n minus 2. So if you just remove a one diagonal, if you just take a say cofactor of this term, say, then you actually remove two diagonal element. That is a12 into something which is a degree less than or equal to n minus 2. Actually, n minus 2 is not less than, exactly equal to n minus 2. That means, if this the characteristic polynomial is like that, the roots are lambda 1, lambda, lambda, then lambda n, so it is just x minus lambda 1 dot x minus lambda n, this equal to this. Now, sum of the roots is just the lambda 1, lambda 2, lambda n is just the coefficient minus of the coefficient of that. If you write in terms of x to the power n, then a1 x to the power n minus 1, that a1 is the sum of the roots. Now, here in the right hand side also, this term, since this term, the remaining terms is degree n minus 2, the coefficient of x to the power n minus 1 is coming from only this part, and obviously the coefficient of this x to the power n minus 1 is just minus of a11 plus dot a1 n. So that's why the trace is the sum of this all lambda 1, lambda 2, lambda n. Now, why this product is a determinant? That is also easy. How do we find the constant term? The constant term is actually, if you put just x equal to 0, so the chi a0 is the constant term. So what is the constant term? Constant term is minus 1 to the power lambda 1, lambda 2, lambda n. Now, here, what is the constant term? Now, constant term of this is just, if you put x equal to 0, so in the left hand side is the constant term. Why this is determinant? Oh, it will be slightly, if you put 0 in this determinant, it will be in the diagonal minus a1 dot dot dot. So you have to just write in the other way, the determinant of this xi minus a, that is nothing but minus 1 to the power n a minus xi. Oh, sorry. No. I just no. It's okay. Fine. No need of that. I write this characteristic polynomial in the wrong thing. So it is minus. Sorry. Okay, it's okay. It's fine. It's fine. So if you, no need of that. Sorry, there's a mistake. So if you put 0 in this, so you will get actually the determinant minus a11 minus a12 dot dot minus a1 and dot dot dot. and this is nothing but the minus 1 to the power determinant of minus 1 to the power n determinant of it. There are n rows. So we get this. So the product of all lambda or all eigen or characteristic roots are equal to that so characteristic roots, the product of the characteristic root is determined and the sum of the root is trace. So again, remember that the characteristic equation for this finite dimensional vector space, for a linear operator and for a matrix is same. So now we are going to discuss the corresponding equivalent form. So now if say this is the characteristic polynomial, the determinant of this, the characteristic polynomial is this. So A is a matrix, n cross n matrix. Now this is equivalent of that, say Ax equal to lambda x, sorry, we just write AV is equal to XV. So existence of that V, so V equal to 0 satisfies this thing. So there exists an V which is non-zero, non vector. So V is 0, AV equal to XV for any x on any V, x on any or any A. But the question is there exist any non-zero vector such that AV equal to XV for a fixed A and X? So A and X is fixed, or the question is A is fixed, and for which values of A, for which values of X, you will get a non-zero V such that AV equal to XV. The answer is precisely this. For we will get a non-zero V for that values of X for which X minus A, Xi minus A determinant is 0. This is if and only. Why? Because this AV minus XV is nothing but is equivalently it is just X, or you write the other way, Xi minus A V equal to null vector. Now this system of equation has a non-zero solution or non-trivial solution if and only if that determinant is 0. So this is if and only. That means for some x, if AV equal to XV for a non-zero V, and that x will give Xi minus A determinant 0. Now the solutions of this is actually, for if there is a solution lambda 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 n that satisfies this AV equal to lambda I V, but obviously that V depends on the lambda I. Now sometime we call that x for which there exists an V non-zero V vector such that Ax equal to XV equal to AV equal to XV, or say lambda V. For that value of lambda, this lambda is called eigenvalue. So lambda is an eigenvalue if there exists an V non-zero V such that AV equal to lambda. Now it is clear that lambda satisfies this for a non-zero V if and only if that lambda I minus a determinant is 0. Now, root of this equation is actually the eigenvalues. No, there is a slight difference between eigenvalue and the characteristic value. The characteristic values are the roots. So roots are the multiplicity. So that characteristic value can repeat. So the characteristic value of A is say 1, 1, and 5. But we say the eigenvalue of this matrix is 1 and 5, all the distinct value. So all the distinct characteristic roots are the eigenvalue. There's a slight difference. So if 1 is the eigenvalue, then obviously 1 is the characteristic roots. If 1 is the characteristic roots, then obviously 1 is the eigenvalue. So if lambda is the eigenvalue, then lambda is the characteristic root. If lambda is the characteristic root, then lambda is the eigenvalue. So what is the difference? So we say the same thing. So if and only just the difference is the multiplicity. In eigenvalue, we don't concept any concept of eigen multiplicity. If I say what are the eigenvalues, you say 1 and 5, the eigenvalues. But if I ask what is the characteristic roots, you will say 1, 1, 5. That's the basic difference. Sometimes they are synonymous in some book, but in the Avina Shankaran they define like that. Now that V is called eigenvector. So to write this characteristic equation, there is no such V. Here, writing in this form, AV equal to lambda V, there is V is there. So this V is called eigenvector. Obviously, that V should be non-zero. Eigenvector should be non-zero. So for a fixed eigenvalue, so how do you find the eigenvalue? To find the eigenvalue, you have to solve this determinant equal to 0. And once we find the lambda, the eigenvalue, then we find V. The eigenvector correspond to the eigenvalue. That means you have to solve this system of linear equations. Now, set of all eigenvalues correspond to a fixed V whatever. What is this? So collect all such V in this vector space, or it may be some with a standard basis, say if it's Fn. And for a standard basis, Fn that and V is same. So from we collect all such V which satisfies this. So lambda is fixed here. Now, is this a subspace? Okay, this is going to a subspace because say V1 and V2 are two elements here. So a V1 equal to lambda V1, a V2 equal to lambda V2. So A of that CV1 plus C1 V1 plus C2 V2 is actually equal to lambda of C1 V1 plus C2 V2. So it is clear. So it is just the distributive property and then pull this coefficient outside, that scalar outside. So it is A C1 V1 plus A C2 V2. That means C1 A V1 plus C2 A V2. But A V1 is just lambda V1. So C1 lambda V1 plus C2 lambda V2. So lambda into C1 V1 plus C2 V2. So this is this C1 V1 plus C2 V2 belongs to that set. So it is a subspace. So subspace. But there's a slight problem. This is subspace, okay, but the element of all this in this subspace is not the eigenvalues, because 0 is here, 0 in this subspace, so 0 satisfies this, but 0 is not to be said to be eigenvalue. So eigenvalue must be non-zero. So that means the set of all eigenvalue, including 0, that and just take the 0, then it forms a subspace. So set of all V such that AV equal to lambda V forms a subspace, and all non-zero V such that AV equal to lambda V is a set of all eigenvalues. So it's from a subspace, and that space is called eigenspace of this matrix or that linear transformation. Now we can for any general, for T is a linear operator, not only linear transformation, linear operator, then we can take a analogous of that, like that. Say there is analogy like that. We will say this transformation. So how do you define this transformation? We define this transformation like that, is xv minus a. I is the not the identity matrix. I is the just the identity linear transformation, identity operator. I is the identity operator. Now, if it is finite dimensional, then there is a corresponding matrix is there, and that corresponding matrix determinant is 0. That means is not invertible. The singular matrix, so not invertible. So we can take the analogous definition for linear operator. Okay, for T from V to V, a linear operator, X is called the characteristic value of that linear operator if Xi minus I is the identity transformation, identity operator on V, minus T is not invertible, non-singular. Now, invertibility is not a concept from the matrix, it is just a concept on the linear transformation or in the function. So this non-invertible, this is not only for this matrix, it is this concept, this idea is also for any function, any linear transformation or any function actually. So if we have such a x such that Xi minus T, that linear operator has inverse does not exist, then we say X as a linear, X as the characteristic root or characteristic value of that linear transformation. So we can generalize this. Now there is no question of matrix and no question of finite dimension. So it's more general definition. So Xi minus T is not invertible. For that X, that X is called the characteristic value of that linear operator T. And if V is finite dimensional, this idea actually merged with the idea of characteristic root of the or characteristic value of this polynomial or matrix. That characteristic matrix, the root of this characteristic polynomial. Here is no polynomial is there. So determinant 0 is the same idea, is more generalized idea, is just not invertible. For finite dimensional case, these two are equivalent. So this is eigenspace. We call this is an eigenspace. So we have an eigenvector and eigenvalues and eigenspace. So we first find the eigenvalue to solve this that characteristic equation. Then we find the eigenvector, that is solution of our system linear equation, and that then we find this eigenspace. And these eigenvalues, that characteristic values and characteristic equations, there is in concept the more general concept for this linear operator in V, not only for finite dimensional. Now some important results. Characteristic roots of a triangular matrix. What will be the characteristic root of a triangular matrix? It is clear that for a triangular, say if it is upper triangular matrix, it's clear that the characteristic polynomial will be x minus, or say lambda. Lambda is historically there, right? Lambda every book. Lambda minus a a1 on all the diagonal elements. This is the characteristic polynomial. Sorry, determinant. So all the diagonal entities are the characteristic roots or eigenvalues. better we say characteristic root. For lower triangular matrix or for diagonal matrix, same thing. For diagonal matrix also, the diagonal elements are the characteristic root. What about symmetric matrix? Now, for a real symmetric matrix, all the eigenvalues are real. For a symmetric matrix, or is it real symmetric? Okay, let's see. If A equal to A transpose, then we say, what is this? Ax equal to Vx. So x is the eigenvalue, characteristic or eigenvalue. Now, whatever. We take transpose of that. And this is just, oh, sorry, we should write AV equal to, say, lambda V, V transpose A transpose, then lambda V transpose. There is no question of lambda transpose. Lambda is a field element. Now V transpose A transpose V, so it is lambda V transpose V. Now what happened? So if also A transpose is A just, so it is AV. AV is lambda V, so it is lambda V. No, sorry. This is why this is why for real symmetric matrix this is why this is real. Okay, we have to take the inner product. Okay, just leave it now. Okay, I'm discussing after this other results. The characteristic polynomial of the transpose of a matrix. What is that? So, what is the characteristic polynomial of the transpose of the matrix? So this is lambda V. So it's a determinant of what is the characteristic polynomial? Say lambda I minus A. This is 0. So take the transpose. So we know the transpose of the determinant is same. So determinant of lambda I minus A transpose is 0. So it is the determinant of lambda I minus A transpose is 0. So that is the same. So transpose matrix and the A and A transpose have the same eigenvalues. What are the characteristic polynomial? The same polynomial actually. What are the characteristic polynomial of the inverse of a matrix? Actually, these are same. Basically, you don't write this equal to 0. So write the, as a polynomial they are same. Not only the equation, as a polynomial they are same. Now, what about the A inverse? Now, lambda I and then determinant, we can write that as what? So A inverse exists, then we take that as, now the characteristic equation are not the same, the polynomial is not same, but the roots are same. Now why these roots are same? If now this is 0, so here it is root, the polynomial itself is equal. For the A transpose, the polynomial itself is equal. Now here it is not the polynomial is equal, here it is the roots are the equal. So if this is so, you just multiply it by the way, for if A inverse exists, then lambda must not equal to 0. So if lambda equal to 0, then A inverse cannot exist. because the product of all lambda, all eigenvalues are determinant. So if I multiply it by A inverse, so this is A lambda A inverse minus identity, this is 0. So now lambda not equal to 0. So take multiplied by lambda to the power 1 by lambda. So then it will get we'll get this lambda to the power minus 1 I equal to 0, and you can just take the minus here. So because it is just minus 1 to the power n, so my lambda to the power minus 1 I minus A inverse equal to 0. So the equation is same. So the roots are sorry, not the equation are same. Sorry, not the polynomial is same, not the equation is same. That is, if lambda is the eigenvalue of A, then 1 by lambda is the eigenvalue of A inverse. So lambda inverse is the eigenvalue of the A inverse. Now, what is the characteristic polynomial of the similar matrix? Now, say what is similar matrix? Say PAP. If P inverse AP is a similar to A. Now this is lambda I minus this. So what is this? So again, you can write I as a P inverse P, and then P inverse AP, and this is just P inverse lambda I minus A P determinant, but this determinant is P inverse. P is a non-singular matrix. Now this is 1. P inverse determinant of P inverse into determinant of P is 1. So again, these two have the same, the similar matrix have the same polynomial, characteristic polynomial. So these are some important result on that characteristic polynomial, or can I say for inverse that polynomial is not same. The roots are also not same. Just roots are the inverse of the root. Now, some more result. There's a one very interesting and important result is this. If A and B are two matrix of order m cross n and n cross m, m less than n, then characteristic polynomial of AB and the characteristic polynomial BA is a link like that. So it is chi and it is x. Chi means it is a characteristic polynomial. Now the proof idea is this. So if for any matrix A with rank R, then there is a matrix P and Q such that PAQ rank factorization thing. So IR null null null. We know that this is the actually the row and actually fully reduced normal form. We have a two non-singular matrix P and Q such that PAQ equal to this. Now by partitioning we can write that Q inverse B P inverse as that. So we just partition like that. Say E and G, Q inverse B P inverse. Now C is the order of R cross R. Now then what happened? Then P A B P inverse is just P A Q Q inverse B P inverse. Now this is just C D 0 0 null null. It's just C D E G into I R 0 0. So it is C D 0 0. And the other way, that Q inverse B A Q is just again that Q inverse B P inverse P A Q, which is C E null null. And from that you find that characteristic polynomial of AB, the lambda is this that variable is that characteristic polynomial of that P A B P inverse, and that is just determinant of lambda IR minus C. Just check this. lambda I m minus r, that determinant, and that determinant is nothing but lambda I r minus c lambda to the power m minus r, and this is similar to that characteristic polynomial of this with BA, the lambda is just lambda I r minus c to lambda to the power n minus r. So this follows the result. Now, what is the utility of this result? Now, if M, A, and B are both order n cross n and n cross n, the same order square matrix, A and B both, then what happens? Then the characteristic polynomial of AB and BA is same. The characteristic polynomial of AB and BA is same if A and B are both square matrix. So it's an important and very deep result that characteristic polynomial of AB and BA is same. Next, characteristic polynomial of a polynomial matrix. So if lambda is a, so from the characteristic polynomial, it should be characteristic value or characteristic root. So characteristic root of a polynomial matrix. That means if lambda is a characteristic root of A, and f is a polynomial, any polynomial, and you can easily check that lambda, f of lambda is a characteristic root of fa. By the way, what is fa? Polynomial matrix. That is nothing but it's like that. Say if f of x is say x cube minus 3x plus 5, that corresponding fa is just a cube minus 3a plus 5i, of the I is the same one. And the most important thing is this: the eigenvectors correspond to the distinct eigenvalues are independent. So if lambda 1 and lambda 2 are two different eigenvalues and corresponding eigenvector v1 and v2, then v1 v2 are independent. Not only that, if lambda 1 lambda 2 lambda k are the distinct eigenvalues, then v1 v2 vk are the corresponding say eigenvector of the lambda 1 lambda 2 lambda k, then the set v1 v2 vk are independent set. That is a very important result. And here we actually talking about that, is this all eigenvalues span this set, then this concept of geometric multiplicity, algebraic multiplicity is there, is the span or not? And that will be in the next video or next class.